case, there is no harm in doing that. There is nothing special about two-dimensional states. We can have three-dimensional, four-dimensional, n-dimensional states. For example, in an interferometer, we've talked about the path of a photon. So the path of a photon is a two-dimensional Hilbert space. The polarization is a two-dimensional Hilbert space. But if we take into account both the path and the polarization of the photon, it becomes a four-dimensional Hilbert space. So we can have arbitrary dimensions. Alright? And this coefficient, which is called a probability amplitude, Ci, is simply the inner product of the state with the basis vector. Right? Any confusions for this point? Alright. So the quantum state can also be written as this Ci is replaced by the inner product. So this is an alternative way of writing down the quantum state. An inner product, which is just a scalar number, could be a complex number, which is the probability amplitude for the basis state, and then you sum up over all the basis states to get the total quantum state. Okay? Now, in two dimensions, this basis vector was generally written as 1, 0, and this basis vector in vector notation was written as 0, 1. So you put a 1 in the first position corresponding to ket 1, and you put a 1 in the second position corresponding to ket 2. So this is our choice. This is a choice that we've made. We could have represented ket 1 by 0, 1 and ket 2 by 1, 0. There's no one stopping you from doing that. But in writing down these physical states, these are physical states. A horizontally polarized photon is something physical. A vertically polarized photon is something physical. So by writing down these physical states in this form, we have, out of our desire, chosen a particular representation for the state. So it's a choice that we've made. Okay? A different person can come up with a different choice. Another person could have written a 1 here and a 0 here for ket 1, 1 here and 0 here for ket 2. It's just using a different representation. But now we are sticking to this representation, so we've made a conscious choice in representing our vectors in a particular way. Okay? So one entry in this representation is 1 and the other entry is 0. Here, there's one entry that is 1 and all the other entries are 0, and there's just one other entry. Now for this n-dimensional space, we can also come up with the representation. Okay? So, ket 1 could be represented by it's again a column vector, okay, in the first position and zeros everywhere else. And I have n elements in total. All of them are 0, just one is 1. Okay? So this is a representation that I am choosing. I can have ket 2 being represented by a 1 in the second location. A ket 3 is represented by a 1 in the third location. And a ket n is represented by a 1 in the nth location. So there are n entries here. The total number of entries in these column vectors is n. So there are n rows to this column vector. So when I write down this recipe, I've chosen a particular representation. Okay? In general, the quantum state psi, written in this representation that we've chosen. Now we've defined a representation, and any matrix or vector that we write has to now conform to the representation that we've chosen. So now we are conforming to this representation. Every vector that we write conforms to this. Okay? We cannot deviate from this representation. If we choose a new representation, we'll have to rewrite our vectors and matrices. So in this representation that we've chosen out of our desire, the quantum state psi becomes C1, C2, C3 up to Cn, right? And these C's are simply the inner products of the state with 1, inner product of the state with 2, inner product of the state with 3, and so on. Okay? Any confusions? So this is how we represent states in general. In the form of a column vector, there are probability amplitudes, and each probability amplitude Cn, Ci is just the inner product of the state with a basis vector. Okay? And we know that this coefficient goes in the first position, this coefficient goes in the second position, this coefficient goes in the third position, and so on. We cannot deviate from this representation that we've already chosen. So this is how we represent states. Now we would like to represent operators. We would like to write matrices for operators. We know that quantum states are vectors, column vectors. And we know that operators, they are matrices that are acting on the column vectors. So now we would like to represent operators in the representation that we've chosen. Okay? This is what we would like to do. Now something from linear algebra that you might remember is that if I have a matrix M and I multiply it with some vector, say V, okay? I get a new vector, W. If this is an n by 1 vector, n rows, 1 column, this is an n by n matrix, then the order of the resulting vector is n by 1. Okay. So this resulting vector will have n rows. The initial vector also had n rows, but this matrix, which is the operator, has n rows and n columns. And I also know that the ith entry in the vector W is just going to be equal to m I j. This is the element in the ith row and jth column of m multiplied by the jth element in V summed up over all of j. Right? Do you recognize this? Anyone who doesn't recognize this fact, I'll be happy to explain. Okay. Suppose I have V, A, B, C, right? And I have a matrix M11, M12, M13, M21, M22, M23, M31, M32, M33, right? And the result is a vector A dash, B dash, C dash. Now how do I compute A dash? A dash is the first row. So I take the first row of the matrix, multiply M1 1 by A plus M12 by this element, M13 by this element, right? So I multiply this with this, I multiply this with this, and I multiply this with this, and then add. I get the first entry here. So this is what I write in shorthand notation. I take the ith row, jth column, ith row, jth column multiplied with the jth row of this column vector, and then add up over all the j's. That is, I go like this. I go like this. I multiply this number with this number, this number with this number, this number with this number, add, and as a result I will get this number. So this is what I write in shorthand notation. This represents matrix multiplication, a matrix that is being multiplied by a vector. Okay? Look at the indices. The first index of M is I, The second index of m is j and the index of this vector is j. So this j comes together, so you add up over all of j, the index that is not being added up pops out as the index of the resultant vector. Okay? So any confusion on this, because we're going to use this quite often. Alright. Has everyone taken linear algebra?
Yes.
Oh, good. So now what we would like to do is we would like to see how the operator admits a matrix representation. What matrix should we write for an operator? We know that we can write a state vector or a quantum state as a column vector. What should we write for an operator? We know the answer is a matrix, but what are the elements of the matrix? What is this element? What is this element? And so on. So this is something we would like to investigate now. Suppose I have a quantum state psi. It is acted on by an operator O. I get a new quantum state, psi dash. Okay? Now I would like to write this initial state and the final state in the same representation. Which means I have chosen my basis vectors and they are represented like this. Okay? So my initial state is represented as a superposition of these vectors. So now if you notice, ket psi dash, which is the final state, is simply operator O acting upon psi. Okay? Now this final state will also be written as all my i's, all my basis vectors with certain amplitudes, right? My initial state psi is written as Ci ket I summed up over all the basis vectors. Okay? So my initial state was written like this. My final state can also be written in the same basis. Right? However, the coefficients will now be different. This is what the operator is doing. It's giving you a new state. The new state is written in some basis which can be the same basis as the original state, in which you represent the original state. So the original state was represented in this basis ket, in all the ket i's. Ket 1, ket 2, ket 3, ket 4. For example, this original state could be C1 ket 1 plus C2 ket 2 plus C3 ket 3 all the way up to Cn ket n. Right? So this was your original state. So after you've acted the original state upon by an operator, you get a new state. The new state can also be written as a superposition of ket 1, ket 2, ket 3 all the way up to ket n. But now the coefficients can change. You have C1 prime here, C2 prime here, C3 prime here, Cn prime here. Okay? Agree? Because that's what the operator is doing. It's changing the state. You know that the Hilbert space is not changing, so the basis vectors remain the same. These vectors remain the same, but now the probability amplitudes are changing. Okay, that's what the operator does. If it were an identity operator, then this C1 prime would be the same as C1. C2 prime would be the same as C2. C3 prime would be the same as C3. All the coefficients will remain unchanged if your operator were just the unit matrix, just the identity matrix. But in general, the operator does something to the state. It can rotate, it can project. So in general, these coefficients, these probability amplitudes will be different. Okay? And we also know that these probability amplitudes, each one of these C primes can be written as the final state projected upon or the inner product of the final state with the basis vectors. Okay? The final state and its inner product with the basis vector gives you the probability amplitude. Okay? This is always true. Look at this expression. The state and its inner product with the basis vector gives you a probability amplitude. The state and its inner product with the basis vector gives you a probability amplitude. So this is a totally general result. Okay? Any confusions? Yeah, something? आपको जहाँ पे समझ आ रही, क्योंकि यहाँ पे अगर आपने लफ्ज़िश खाई तो फिर ठोकर खा के गिरेंगे, फिर उठना बहुत मुश्किल होगा. We can go slow here, but we really need to be meticulous here. We cannot lose any step.
Sir?
Yes.
Initial equation की I just reference matrix multiplication.
This one?
Raji.
Ji.
This is matrix.
Yeah, I'm going to use this somewhere. Okay. So the coefficient, so the final state, psi dash, can be written as a column vector. Now the entries in this column vector are, what are the entries? C1 prime, C2 prime, C3 prime, all the way up to Cn prime. Now we would like to find out these entries. What are these entries? And what is the matrix representation of the operator? What is the operator doing? Okay. Now look at this expression. Okay. The C1, the C iota prime is a coefficient in the final state, a probability amplitude in the final state is given by the overlap or the inner product of the final state with any basis vector that you're interested in. Now this expression can also be written as bra I. This psi prime is the new state, is the operator acting upon the initial state. Okay. Now this initial state, so what I do, I just write this bra I, write this operator O. Now I can represent this initial state somehow. How can I represent it? The initial state is just this state. Okay. So this initial state, I can write this as some coefficient Cj ket j summed up over all of j's. I'm not writing I here because this ket, this quantum state, has all the possible values of j. I'm not writing I here because I've already written here. Any confusions at this level? I can repeat, no, so don't be shy. I do, okay. Any confusions up to this point? Alright. Now this psi, we know that this psi equals C1 ket 1 plus C2 ket 2 plus all the way up to Cn ket n, right? And the shorthand for this is Cj ket j summed up over all of j. Okay, so this is your initial state with coefficient Cj. Now I just take this expression and put it in place of this psi. That's what I've done. And I don't use the index I here because I is something fixed. Okay, I focus my attention on Ci prime. I'm picking up one of these coefficients like C3 prime. So there's a 3 here. But here I want to use all the indices 1, 2, 3, 4, 5 all the way up to n. That's why I use a different index here, j. At one point this j, one of these indices will be equal to I. But I'm using all the indices because the original state is expanded in all the indices C1, C2, C3 all the way up to Cn. But I don't use I here. I use a different label here. Okay? Any confusions up to this point?
सर लेकिन बेसिकली इसमें आप कह तो सिर्फ यही रहे कि इट्स द सिग्मा j operator O operating on C of j.
It's the operator acting on this sum.
सर वो तो बात सही है लेकिन वो I inner product with ket j, it will only allow if j is equal to I.
Let's see that. अभी हम आगे वो देखेंगे. ठीक है, यहाँ पे बात समझ आ गई? ये समझ आ गई? अब ये एक कैट है ना, ये क्वांटम स्टेट है, और ये क्वांटम स्टेट इस ब्रैकेट्स में पैरेंथेसिस में जो लिखे इसके बराबर है. ठीक है, मैंने इसकी जगह ये पूरा कंप्लीट इसकी सुपरपोजिशन फॉर्म दी, because I want to write everything in terms of the basis vectors. Okay? So is this clear now? I give you half a minute to brood over it. Just think over it. I don't want to go fast. I just want you to think over it. ठीक है, हम क्या करना चाह रहे हैं? हम नई ट्रांसफॉर्म स्टेट के कोएफिशिएंट्स मेजर करना चाह रहे हैं, एक के बाद दीगरे, एक के बाद दूसरा. पहले हम C1 प्राइम मेजर करना चाह रहे हैं, C2 प्राइम मेजर करना चाह रहे हैं, C3 प्राइम. तो हम कोई सा Ci प्राइम मेजर करना चाह रहे हैं. Ci prime is given by this expression, but this psi dash is a vector, right? It's a whole state with all the bases, different probability amplitude of all the bases. So, but this is the original state being acted upon by the operator. Now, the original state is a superposition of all the basis vectors. So, I replace the original state by this sum, this linear sum, this superposition. That's what I've done. Okay? This means that my Ci prime is given by I operator O. Now this is the sum over all of j. So I can take this sigma sign outside. And this Cj is just a number, it's a scalar. So it's porous, I can move it anywhere in this expression. And this is a ket. So this has to remain where it is. Okay? So I just do this percolation. I write ket j here. I write Cj here. And I take the sigma sign summed over all j here. Okay? Okay? Now what does this mean? This is a number Cj. It is the probability amplitude of the jth basis vector in the original state. Okay? This is just a number, just a scalar. Whereas this is also a number, right? It's an inner product. It's just a number, it's a scalar. So now I have two numbers being multiplied by one another, and I'm taking the sum. Now if I represent this number, I just represent this number by O operator I j. I just represent it like this. Okay? Because it has two indices, I and j. So I put I, whatever appears in the bra, as the first index, and j as the second index. I just represent, or I substitute this number by this label, right? It's Oij. Okay? And this expression then becomes sum over all of j, O, ij, cj. Okay. Now, if you look at this expression and compare it with this expression, do you find any similarities? So, this element Oij turns out to be an element of the matrix representation of the operator O in the I, j position, which means the ith row and the jth column. So if I would like to write the operator O in matrix form, the size of this matrix will be n times m, and the elements of this matrix will be O11, O12, all the way up to O1n. Second row, O21, O22, all the way up to O2n. Third row, O31, O32, all the way up to O3n. And I have many other columns, many other rows. So the last row will be nth row, first column, nth row, second column, nth row, nth column. So this will be the matrix representation of the operator O. It will have n into n square elements. Each element is labeled by a row and a column. Okay? For example, O11 is an element in the matrix for the operator. And this is a representation of the operator, a matrix representation of the operator that conforms to this ordering of numbers. Okay, that conforms to this representation. So this is the matrix representation, and each element O11, O12, each one of these n squared elements is given by this inner product. So this O11 will be bra1 operator acting on the state 1 and its inner product with the state 1. I just want to rub this a little bit so that, okay. This element is just 1, right? This element one, okay. This element, second row, first column, second row, nth row, so this is the matrix representation of the operator, and we have specified each and every element of this matrix. So what is the ijth element? The operator acts on the jth basis vector to gives you some new state, and you find the overlap of that state with the ith vector. And I'll show you more examples of this. But this is the general scheme. I give you 1 minute to reflect. मुहासबा करें अपना भी, ब्लैक बोर्ड का भी देखें क्या लिखा है. Let's start with something really simple. Suppose I have a two-dimensional Hilbert space and I define a representation. Okay? And my representation is defined somehow like this. Cat H and cat B are my basis vectors, right? And I represent cat H by 1, 0 and I represent cat B by 0, 1. Okay. Now what I would like to do, I would like to find out the matrix representation of the operator PH. Okay, horizontal projection operator. In order to find out the matrix representation, I would like to find out its elements. The elements in the matrix. How many elements would this matrix have? 4. Because it's a two-dimensional Hilbert space, it will have 4 elements. So PH in general will have 4 elements. Okay? The first element will be bra H, PH, H, bra H, PH acting on cat B, bra H, PH, bra B, PH acting on H, bra B, PH acting on B. So these are the 4 elements of the representation of the operator. Okay, just in complete consonance or in complete concordance with what we wrote over here. Okay? Yes.
So can we work in 1 and 2, 1 cat?
Yeah, you can write this as 1, you can write this as 2, it doesn't matter. I can call this cat 1, okay? I can call this cat 2. Okay? So this becomes 1, 1, 1, 2, 2, 1, 2. Okay? Now, I have to employ some physics to tell me what the projection operator does. The projection operator acts on cat H to give me cat H, and the projection operator acts on cat B to give me 0. So, if I want to find this, bra H, PH acting on H is inner product of H with itself. This is 1, this is 0, this is 0, this is 0. So the matrix representation of the projection operator is this. Okay? This element is 1, this is 0. कौन सा? ये वाला? ये? Right? PH acting on D gives you 0. PH acting on H gives you 1, but its overlap with B is 0. So this is the matrix representation of the projection operator. And we also learned that this is equal to cat H, bra H. This is something we learned earlier. So if I would like to write this cat H as a column vector in the representation that I've chosen, then this bra is a row vector. It's just a transpose, the complex transpose of this vector, so I get a row vector. Now if I do matrix multiplication for this column vector and row vector, I will get the same form for the matrix. Okay, so everything is tied together. Let's look at another example. Any questions? So far so good, easy. Everything is flowing like crystal clear water. It should be easy. Right? Another example. Rotation operator which rotates about the z-axis by say 60 degrees. So I would like to find out the matrix representation of RZ by 60 degrees. Okay? A rotation operator. Again, it's a two-dimensional space. So I choose the same representation as I've chosen here. Okay? I choose the same representation, the same basis. So I would like to find out the effect of RZ through 60 degrees on cat H. What is the result? Cos of sine of 30, 1 over 2 cat H plus under root 3 over 2 cat V. Right?
Yes.
Okay? Is the state normalized? Is this state normalized?
Yes.
Yes, because modulus square of this is 1 by 4, modulus square of this is 3 by 4, so the probabilities add up to 1. So I choose one of the basis vectors, find the output state when the operator acts on one of the basis vectors. Now I choose the other basis vector and I find out what happens when RZ acts on the other basis vector, cat V. What do I get? This is 60 degrees. Cos of 60, sine of 30. Right? This is what I get. Now the rotation operator will have a matrix representation RZ pi by 3 in the same representation that we've already chosen, given by RZ. I'm not writing this pi by 3 over and over again. I can if you really insist, however. So I have cat 1 for H. Okay? This is the first element. The second element will be RZ pi by 3 cat. Now this element is going to be Ravi RZ pi by 3 acting on H, B RZ pi by 3 acting on B. Okay, so these are the four elements. Now I can use the physics. What happens to the horizontally polarized photon or this basis state when it is acted upon by the operator? I can use this physics to find out what these elements are going to be. So what is this first element going to be? Half. What is this element going to be? This element. Minus under root 3 by 2. Okay? This element going to be under root 3 by 2. What's this element going to be? 1/2. RZ. Okay, so now I have found a matrix for the operator in the representation that we've all decided upon. Which means I found a matrix for the operator in a particular basis. Now if you look at this operator and its representation, can you tell me what the adjoint of this operator is? RZ adjoint. In order to find the adjoint, you take the transpose and the complex conjugate of every number. So all of these numbers happen to be real, so you just have to take the transpose. So the adjoint is half. This number goes here, minus under root 3 by 2. This number goes here, under root 3 by 2. So this is the adjoint of the operator. Okay? Now can we find the inverse of this operator, of this matrix? that's easy to do.
Joint equally.
So if you invoke your skills from linear algebra, RZ pi by 3, you want to find the inverse of this matrix. First you find its determinant, which is 1. So 1 over the determinant, which is 1, and then you multiply it with the matrix of the cofactors. Right? The matrix of the cofactors is to keep the diagonal elements unchanged, and you just reverse the order of the off diagonal elements. So this is, but this is actually equal to the adjoint. Right? So what is such a matrix called? Whose adjoint is equal to its inverse? It's a unitary matrix. It's a rotation operator, so it must be a unitary matrix. It just rotates the state. It doesn't change its amplitude. It may add a phase factor, but it doesn't change the length or the norm of the state. Okay. Any questions?
Sir, we will work in two-dimensional like this.
No, why not? We will work in multiple dimensions.
Say 1 over the dimension.
1 over the determinant. Determinant is the 1 here. Okay, now one small question for you, and I give you 5 minutes to solve this. The question is, I have a two-dimensional system, okay, but I change my basis vectors. My basis vectors are now ket 45 degrees and minus 45 degrees, right? So this is represented as 1, 0, whereas this is represented as 0, 1. Okay? There's nothing special with cat H and cat P. I can call this cat 1, I can call this cat 2, right? This is also a legitimate basis, right? There are infinite possibilities of bases. Any two vectors that are 90 degrees apart can form a basis for this two-dimensional space. Okay? So there's nothing special with cat H and cat P. Now this is the representation that I want to work in. Now what I would like to do, I have PH, the projection operator that projects states onto the horizontal axis. I would like to find its matrix representation in this basis. So what I would like to find out is 45 degrees PH acting on 45, right? 45 degrees PH acting on minus 45 degrees, minus 45 degrees PH acting on 45 degrees, minus 45 degrees PH acting on minus 45 degrees. So I give you 5 minutes, please try to find out this matrix, which represents the same physical operation but in a different basis. So let me start this for you. I want to find out the effect of the horizontal projector on 45 degrees. Okay? Now this is governed by physics. Physics tells me that if I have photons that are coming in by 45 degrees polarization, what happens if I pass them through a horizontal polarizer? So what happens is that pH acting upon 45 degrees, what I would need to do, I would like to write pH for my convenience as 1 over under root 2 cat H plus cat V. Okay? Because I want to look at the physics. Now I know that the output is just going to be 1 over under root 2 cat H. So I fall back onto the horizontal vertical basis because it's easier to think in that basis. I need not do it if my mind is so intelligent that I can twist my frames of reference in my mind easily, but it's easier to think in the horizontal vertical basis. So I express this cat 45 degrees onto the horizontal vertical basis and see that my output is cat H. Okay? Now I would like to find the projection or the inner product of this with cat 45, right? But this bra 45 degrees is 1 over under root 2 cat bra H minus bra V, right? And this is simply 1 over under root 2, okay? And the result turns out to be 1 over 2. Okay? So this number is 1/2. This number is also 1/2. I'm missing the step. This is 1/2. This is minus 1/2, I think. Okay? सारे 1/2 आ रहे हैं, सारे 1/2 आ रही हैं। Alright? So my projection operator PA is equal to, okay, in the new representation, in the basis of 45 degrees and minus 45 degrees. ये सारा आपको solve करके दिखा दूं? Okay, is this clear? Right, so this is plus with this and that. Right, okay, let me calculate all the 4 elements for you. Alright, the second element, I would like to calculate this element now, okay? So what I need is pH acting on minus 45 degrees is pH acting on 1 over under root 2 cat H minus cat V, okay? 1 over under 2 cat H is the answer, right? So 45 degrees pH acting on minus 45 degrees. Now this bra 45 degrees is 1 over under root 2 cat H plus cat V. Okay, and this I've already calculated. 1 over under root 2 cat H. The result is 1/2. Okay, so this element is also 1/2. Okay, I would now like to find out this element, but this I've already calculated. Okay, so minus 45 degrees pH acting on plus 45 degrees is minus 45 degrees is 1 over under root 2 cat H plus minus cat V. This is 1 over under root 2 cat H. The result is 1/2. Okay? So this element is also 1/2. Now let's look at this element. Minus 45 degrees pH acting on minus 45 degrees. Minus 45 degrees is 1 over under root 2 ket H minus ket V, and this I've calculated here. This is 1 over under root 2 ket H. So my result is 1/2. So the projection operator is represented by half in every location in the new basis that I've chosen. In the new representation. In the old representation in which the basis vectors were ket H and ket V, my projection operator was 1 0 0 0. Physically these projection operators are identical. It's just a change of basis. Okay? They're being represented in different bases. Now what does this physically correspond to? Suppose I have a polarizer. Okay? And this is the horizontal axis. If I choose my, now look, listen to this very carefully. This is the axis, the physical axis of the polarizer, the transmission axis. Any polarization that is parallel to this axis will go unscathed. Now, if the input is parallel, it will go out unscathed. Anything that is perpendicular to this will be completely blocked. Polarization perpendicular to this will be blocked. Now, out of conventional wisdom, you like to write the matrix for this element in this form. Okay. Now suppose I take the same element, just the same element, and I rotate it by 45 degrees physically. Okay. So now my polarizer is the same element, but this axis is now at 45 degrees with respect to the horizontal. Okay. Alright. Now, if I choose this to be the x-axis, okay, if I choose this to be the x-axis, the matrix of this element in this rotated frame will exactly be equal to this. Okay. However, if I remain in this original axis, in the original basis, if I say that, oh no, my reference frame comprises a horizontal axis here and a vertical axis here, then in this representation, this object will have an operator given by 1/2, half, half, half. Physically, it's just rotating the frame of reference. If I take this physical polarizer and I choose my x-axis to be like this and my y-axis to be like this, then in this basis, the operator or the matrix representation of the same polarizer will change to something different. So depending upon what is my basis, I can represent the same element in different bases differently. The matrices will appear differently, but then my states have to be written in the same basis. So the states have to be written in a particular basis, and the operators acting on the states must conform to the same representation. Okay? Now I have something very interesting for you in these last 10 minutes before our break. And remember, you can find the matrix for this rotated polarizer just by having ABCD, right? And inputting a state that is 45 degrees polarized and inputting a state that is 135 degrees polarized. You know what the outputs are, and the A, B, C, D's that you will get will exactly be identical to this. Okay? Now I would like to tell you about a similarity transformation. Or a change of basis. Any quantum state psi. Now the quantum state is something physical. You don't need a representation to describe the state. Even if there were no basis, even if you didn't choose a basis, the state still exists. So the quantum state is something objective. Okay? The state is something objective. It's objective reality. But when you put it in a representation, as a column vector, this is subjective. You can choose a different basis, another person can choose a different basis. So the representation all depends upon the basis you choose. But the quantum state, the physical reality still exists, oblivious of what representation you choose. Okay, so this is an objective reality. The quantum state is an objective reality. Now this quantum state can be written as Ci, Zi, summed up over all the i's. Okay? Here you've chosen a basis which comprises the cat i's. Okay? However, the same state can be written in a different basis. So the same state can also be written as some I tilde, Ci tilde, right? A different basis, where this tilde represents some other basis there, some other set of basis vectors. For example, for a two-dimensional Hilbert space, one set of basis vectors are cat H and cat B. Right? This is one set of basis vectors. Another set of basis vectors, one tilde, 45 degrees polarized light, and two tilde, minus 45 degrees polarized light. So this is a different basis from this basis. But the same state can be represented in either this basis or in this basis. Okay? Now what is this coefficient equal to? This Ci prime, Ci tilde is equal to the overlap of the state with I prime, with I tilde, right? Now what is this psi? This psi can be written in this form, in the original basis. Okay? So I can write this psi as, I keep this bra as it is. This state I would like to represent it in the original basis. So I replace this psi by the original prescription, but I use a different label J for reasons that I've already explained. Clear? Now this Cj is just a number. Okay? And what is Cj? Cj is this probability amplitude in the original basis. I would like to find out the probability amplitudes in the new basis in terms of the probability amplitudes in the old basis. That's what I would like to do. So I just take this sigma sign out. This I tilde j Cj. This is my Ci prime, Ci tilde. Is this like a does this look like a matrix equation? Yes, it does. So this is a number. Okay? Look at the labels J and J here. And I'm summing up over all of J. And this is I tilde, which is just appearing here. So this Ci tilde just equals some matrix whose elements are given by Sij multiplied by Cj summed up over all of them. So what I have here, last couple of minutes, I cannot leave the discussion at this stage. So the matrix, the state is written as C1, C2, all the way up to Cn in an old basis, in the old basis. Okay? In the new basis, the probability amplitudes are C1 tilde, C2 tilde, all the way up to Cn tilde, and in between we have a matrix. Okay? This element is S11, S12, all the way up to S1n, S21, S22, all the way up to S2n, likewise Sn1, Sn2, all the way up to Snn. So this is an expanded form of what I've written in a condensed form over there. And each of these elements, Sij, is simply the overlap or the inner product of the basis, old and new basis vectors.
So this I in S is equal to algebra.
Sorry?
Is the I in S algebra?
Where? So each element is an inner product of the old basis vector with the new basis vector. For example, S34 is the inner product of 3 tilde with 4. If I am talking about a two-dimensional Hilbert space in which these are my choices, then my S matrix, my similarity matrix, will simply be given by my new is 45 degrees H, 45 degrees V, minus 45 degrees H, minus 45 degrees V. So this will be the matrix that will take a vector from the old basis to the new basis. And we'll do more examples of this in our next section. So let's have a 15-minute break. We'll meet after 15 minutes with the quiz. Okay? Outer product in which the label here is the same as the label here.